Okay, hello everyone. My name is Ferdinand Tadi, and my name number is 2305531 and 78. I'm here to presentation about metallurgy, and the topic is testing and inspection of metal, the quest for quality. And my presentation is from the book source is Metallurgy for the Non-Metallurgists, second edition, edited by Arthur C. Reader. And the content is in the 7.1 is the metallography, in the 7.2 is a hardness testing, in the 7.3 is tensile testing, in the 7.4 is fracture toughness, in the 7.5 is impact testing, in the 7.6 is fatigue testing, and the 7.7 is a non-destructive testing. Testing and inspection of metals, the quest for quality. The level of quality of a product or service may be judged by the customer based upon conformance to the relevant set of specifications or standards, or lack thereof. Quality may be defined or judged from a subjective comparison against an ideal standard or similar product, or it may involve a quantitative feature of characteristic of a product or service. This is the traditional definition of what is called product quality. Quality can also be defined by the degree of variability and concern in the process of service. This concept of quality is the underlying basis of statistical process control. All products and service have variability because it is impossible for all units of a product or service to be made exactly alike. A simple example is the cutting of a bar to a specific length. If several separate cuts are made, the resultant piece will vary in length by some measurable amount. Variability may be difficult to measure when a product is made by precision equipment, but variability is always present. In the 7.1 is a metallography. You can see the picture of 7.1. The macrograph of the Elbogen iron meteorite prepared in 7808 by Count Whitman Stanton and scrapers using heavy etching in nitric acid. After rinsing in the water and drying, printer's ink was rolled on the etched surface, and the sample was pressed onto a piece of paper. In the picture 7.1 is the figure of Jose Ramon Villela. Uh, uh, the 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 Jose Ramon Villela is the distinguished metallographer who understood the need to prepare representative surface in metallographic examination. In the picture 7.3 is an example used by Villela to illustrate the effect of disturbed metal on the appearance of perlite. In the A is a polished surface covered by a layer of disturbed metal. In the B is the same field after removing the layer of disturbed metal by alternate polishing and attaching, revealing the true structure of lamellar perlite. Attached in pictorial region, original magnification is a 7000. In the 7.2 is hardness testing. You can see the picture of 7.7 is the diamond cone brawl indicator. In the shown on approximately 2x. In the B, you can see the comparison of all and new US diamond indicators. The angle of The new indenters remains at 120 digit, but it has a larger radius closer to average ASTM specified value of 200 Newton meter. The old indenter has a radius of 192 Newton meter. The indenter with the large radius has a greater resistance to penetration of the surface. And the figure is 7.8 is a micro hardness indenters. In the A is a schematic of the square beds diamond pyramidal indenter are used for the figures test and example of the indentation it produces. In the B is a schematic of the rhombohedral shaped diamond indenter used for the knob test and examples of the indentation it produces. The the indentation shown in the right side of both in the A and in the B were made in the ferrite paste of a ferritic martensitic high carbon version of 400 and 430 stainless steel with the left to right 500, 300, 150 and 10 DF test forge. Original magnification is 250 and 300 respectively. In the figure 7.4 is a dual specimen mount for sample holder. In the figure 7.5 is a Brinell indentation process. In the A is schematic of the principle of the Brinell indentation process. In the B is a Brinell indentation with the measuring scale in the millimeters. In the 7.3 is a tensile testing. You can see the picture of 7.11 is a components of an electromechanical in the screw driven testing machine for the configuration shown. Moving the lower intermediate head upward produces tension in the lower space between the crosshead and the base. In the figure 7.12 is a schematic of a basic servohydraulic closed loop testing machine. In the 7.10 is a little giant hand cranked and steel tester of tennis also. In the Kirka 1900. In the 7.13 is an example of gripping method for tension test piece. In the A is a round specimen with threaded grips. In the B, butt end specimen constrained by a split collar. In the C is a gripping with serrated wedges. In the D is a seat specimen with serrated wedge grip. Hatch region in C and D shows but practice of wedges ascending below the outer holding ring. In the 7.4 is a fracture toughness. In the 7.14 is a test setup using wedges grips on. In the A is a flat specimen with axial extensometer and in B is a round specimen with diametral extensometer. In the 7.15 is a throat thickness crack of a length 2 are oriented perpendicular to the applied tensile stress. In the omega, the shaded region surrounding the cracks represent the material that carries little or no loads due to the presence of the defect. In the 7.16 is the DSS scanetady after a sudden fracture due to rapid growth of a crack that started in the hull wall. In the 7.17 is in the A is a effect of thickness on the state of stress and fracture toughness at the crack tip. In the figure 7.11 in the 7.18 is the stress distribution ahead of a crack in which. In the 7.19 is an example of specimen tapes used in the KLC fracture toughness test. In the ISTM E399 RF 7.9. In the A is a single edge notch band, SAB. In the B is a compact specimen in the C and T. In the figure 7.20 is a specimen orientation scheme showing the longitudinal and long transverse and short transverse direction. In the 7.5 is impact testing. You can see the picture 7.21 is a standard impact testing approach. In the impact test, the specimen is subjected to dynamic shock loading to evaluate the response of a material to rapid change in loading, such as the experienced by an axle shaft when a car hits a cog hole. The amount of energy required to break the specimen is absorbed by the pendulum, which reduces the height to which the pendulum rises. The difference between the height to which the pendulum can rise unimpeded, h, and the height to which the pendulum rises after breaking the specimen, h, represent the energy absorbed in the breaking the specimen. This energy is a h minus h, expressed in the Newton meters or joules or foot-pounds is the cold. In the 7.6 is fatigue testing. You can see the picture 7.22. In the A is impact on a specimen, and in the B is isotope. And the A, sorry, and the A is a HRP, and the B is isotope. In this picture 7.23 is a laboratory simulation of the multi-stage fatigue process. In the 7.24 is a stress versus load cycles to failure surface for bend. In the picture 7.25 is a fatigue rate growth per fatigue cycle or DI per DN versus stress intensity variation or delta K per cycle. The C and N are constant that can be obtained from the intercept and slope, respectively, of the linear log di per dn versus log delta k plot. This equation for fatigue rate growth is a useful model for mid-range of delta k. In the 7.7 is a non-destructive testing. In the picture 7.28 is an effect of crack on the pattern of eddy current flow in a pipe. And then it says the table of comparison of some non-destructive testing modes. You can see the method, characteristic detected, advantage, limitless, and example of use. In the picture 7.26 is a liquid penetrant test for surface cracks. In the A is an opaque crack doused in penetrant liquid by capillary action. In the B is excess surface penetrant is removed. In the C is developer draws out penetrant liquid on forms a visible indication of the surface crack. You can see the table 7.2 is relative use and merits of various non-destructive testing modes. And you can see the picture parameter, ultrasonic, X-ray, and you can see any test methods. In the ultrasonic, X-ray, eddy currents, magnetic purchase, and liquid penetration. In the picture 7.27 is an electromagnetic yokes showing position and magnetic fields to detect discontinuities parallel to a well beat. Discontinuous across a well beat can be detected by placing the contact surface of the yoke next to an on either side of the beat. In the rotate yoke about 90 degree from position shown here. And this all my presentation, and thank you.